Alright, welcome back. So today what we're going to be looking at is a new concept for acids and bases, and it is called the Bronsted-Lowry acid and base concept. So last year we would have learned the Arrhenius theory based on acids and bases, and we learned there was lots of limitations with that, whether it was the normal Arrhenius theory or even the modified Arrhenius theory. So this Bronsted-Lowry theory kind of fixes the problems with the Arrhenius theory. And that is because, first of all, the Bronsted-Lowry theory focuses on the role of an acid and a base in a reaction rather than on acidic or basic properties of the aqueous solution. So this is where it actually looks at the reaction as a whole and not so much will it turn blue litmus paper red or will it have a pH or something like that. So our new definition of a Bronsted-Lowry acid is going to be a chemical species. So this can be an anion, a cation, or an entire molecule that loses a hydrogen ion. And we call this a proton donor. So the reason it's called a proton because a hydrogen ion, it has 1 proton, 0 electrons, and 0 neutrons. So that is why the hydrogen ion is normally considered a proton, is just because it only has just the positive proton inside of its structure. Now, so a Bronsted-Lowry acid is going to be a hydrogen ion or a proton donor, where a Bronsted-Lowry base is going to be a species that gains a proton, or we're going to call a proton acceptor. So this is a little similar to electrochemistry, where electrochemistry we worried about the transfer of the electrons. Now for our acid and base section, we're going to worry about the transfer of a proton or the hydrogen ion. So a Bronsted-Lowry reaction comes down to a competition for protons, and this results from a proton transfer from the strongest acid to the strongest base present. And then of course this forms new acids and new bases. So for example, we've seen this before. So if we had HCl, hydrochloric acid, dissolved in water, what's going to happen is we know this is going to be the acid, and this is going to act as the base. We're going to get this hydrogen ion transfer from our hydrochloric acid to our water molecule. And of course this creates our Cl minus and our hydronium ion. Now I use a single arrow here and not an equilibrium because we know HCl is a strong acid, so it ionizes 100%. Now the strength of our new Bronsted-Lowry acid and base definition is that water doesn't need to be involved in the reaction. So in our modified Arrhenius theory, we had to show water being present in the reaction with water to produce hydronium to identify as something either an acid or a base. But now this one, it doesn't have to be present. So we can get, for example, HCl reacting with ammonia. Now in this example, we know HCl, hydrochloric acid, well, it's an acid. And we're still going to get this transfer of hydrogen from one species to the other. So if we follow the transfer of that hydrogen, what we're left with is Cl minus. And now our ammonia NH3 is going to pick up an extra hydrogen, so we go NH4. Because that hydrogen had a positive charge, now this has a charge and it turns into the ammonium ion. So in this reaction, hydrochloric acid obviously acts as the acid, where the ammonia now acts as the base. We have our proton donor and our proton acceptor. So that is the strength of this Arrhenius acid and base reaction, is that now we just classify things on how they react. So one thing to really keep in mind though is that this concept does not define a substance as an acid or a base. It only defines if they are acting as an acid or acting as a base. So that's the major difference right now in our Bronsted-Lowry concept. It's about how they act. So a substance may act as an acid or base even if its aqueous solution does not change the color of litmus. And that is one thing that we learned, or you guys learned now for a while, is that an acid or base needs to change the color of litmus. Well, now what this Bronsted-lowry reaction is saying is that it doesn't necessarily need to do that, although we need to look at the reaction to see if there is a transfer of the proton. And of course, some substance may act as an acid in one reaction and may act as a base in another reaction. And we're going to look at this example. So baking soda, its sodium hydrogen carbonate, forms a basic solution when we mix with water. Now, first thing we have to realize is that sodium hydrogen carbonate, it's an ionic compound. So it will dissociate before it can react. So that means as soon as we put sodium hydrogen carbonate in water, it's going to dissociate to produce the sodium ion and the hydrogen carbonate ion. Now, just looking at our two products right here, so in order to form a basic solution in water, we need to have a reaction with water. So that means we can either have the sodium ion attracting a hydrogen, or we're going to have our hydrogen carbonate. So the way to remember which one is going to either act as an acid or a base, where we're trying to attract the hydrogen ion, the negative will attract the positive hydrogen ion. So what we can do now is show how a basic solution can come about, is that if we know we can transfer our hydrogen over to our hydrogen carbonate to form H2CO3 plus OH minus. So this is that's our basic solution. Now when we look at what water is acting like in this example right here, water is acting like the acid, where now our hydrogen carbonate is acting like a base. But because of this reaction, we get our sodium hydroxide, or our basic solution, being formed. So that is how we've done this before in the past, showing how basic and acidic solutions can form based on these reactions. But now all we're doing is just showing that, okay, we can get this hydroxide ion being formed, which will then in turn make a basic solution. But it's because the water molecule acts as the acid, losing a hydrogen to the hydrogen carbonate. Now, just showing as well how some substance can act as an acid in one reaction, a base in another. If we have our hydrogen carbonate and dump in some sodium hydroxide, so remember sodium hydroxide is aqueous, that's just Na plus and OH minus, right? When we write out the major entities, not so much plus. And remember, hydroxide is a strong base. It is the definition of a strong base. So that means if hydroxide is the strongest base present, that's going to act as a base. This is going to act as an acid. So we're going to get our hydrogen transfer like this, and we get CO3 2 minus plus H2O. And we can tell now, as it's saying, that by adding sodium hydroxide to the solution, we can help reduce its pH or neutralize it. And this is why. So our hydrogen carbonate is going to lose its acid, and it's going to basically react with hydroxide to produce our carbonate ion and of course water. And because we're producing that, that is basically our neutralization reaction. So this is how some substance can act as both an acid and a base, which we've done this before with the modified Arrhenius theory and stuff like that. Now our next lesson, we're actually going to look at predicting what reaction will occur. So if we dump hydrogen carbonate in water, what will actually occur. But that'll be for next lesson. Basically what we're doing for this one right here now is we're just going to be looking at reactions, and we're just trying to figure out what is acting as the acid and what is acting as the base. So our next little bit is what we're going to do is looking at identifying conjugate pairs and something called amphiprotic substances. So we'll kind of get to what they mean now in a bit. So a substance that appears to act as both a Bronsted-lowry acid in some reactions and a base as another, well, we call these amphiprotic. So that's that definition right there. So it'd be all right if I spell this right. There is didn't need to make it that long. There is another word that might show up as well. Instead of amphiprotic, is this word called amphoteric. So they both mean the same thing. So these substances act as a acid in one reaction as a base in the other. So for example, our hydrogen carbonate, where we just showed how it can act as both an acid and a base, we will call that amphiprotic or amphoteric. Both are interchangeable. Now, how to identify these here? It's most polyatomic ions with at least one hydrogen in it. So when we look at hydrogen carbonate, because it can lose this hydrogen right here acting as an acid, or that negative charge will attract the hydrogen, act as a base. Hydrogen phosphate, same thing, it has this hydrogen it can lose to act as an acid, and that negative charge can attract the hydrogen ion, so it can act as a base. So if you want to write that down, is the negative charge, or the fact that it has so many oxygens which are very electronegative. So a negative charge can attract the H plus ion, and it can lose its hydrogen. As well. Now, of course, there is a way to check for amphoteric species as well. So if you do go to your data booklet as well, you'll notice on page 8 and 9 we have acid formula, and we'll get to this word right here, conjugate, what that means. But we have acid formula and then, of course, base, right? So when we look at substances, like, for example, HSO4 minus, notice here how it's on the base side, but the HSO4 minus also shows up here on the acid side. So it's in both columns. Same thing with our dihydrogen phosphate, H2PO4, is on our base side right here, but it also shows up on our acid side, H2, oh sorry, that's not the one right there. I'm looking for H2SO4 minus. H2PO4, sorry, shows up on the acid side right here as well. So you notice that if it shows up on the acid side in our data booklet and the base side, then that's amphoteric, where it does show up twice. So it can act as both an acid and a base. Now, of course, the advantage of this theory, it allows us to define acids and bases in terms of the reaction rather than just are they going to change litmus a certain color or do they have certain properties. So right now, it doesn't look at how or explain why a proton is donated or accepted, but next week we're going to look at how to actually calculate that. So just for right now, we're only looking at defining something as either acid or base, and next week we're going to look at actually calculations, hard evidence on how we can define them through calculations and using ice tables. So for example, just our first little exercise right here is actually looking at equilibrium reactions and identifying the acid and the base. So what we're doing is just kind of looking at our reactants and products and figuring out where that hydrogen went. So for example, notice that we have HF and SO4 minus, and our products we got F minus and HSO3 minus. So we can tell the hydrogen left HF and went here. So there's our acid and there's our base for that reaction. So I just want you to pause the video and see if you can go through and get B, C, and D following the hydrogen. And the answer is going to go up in about 3 seconds. And we have all of our reactions like this. So in B, we got the acetic acid acting as the acid, the carbonate ion acting as the base, because we can tell the hydrogen is leaving here and going over there. Same thing with C, we can tell the hydrogen is leaving our phosphoric acid and going to the OCl minus ion. And same thing with D, we can tell that the hydrogen sulfate ion is losing its hydrogen to the hydrogen carbonate ion, and so on. So that's just kind of the main thing right there, where we can actually, as long as we have our reaction, we can see what is acting as the acid and the base. Now, for example 2, we're going through the amphoteric species of the hydrogen sulfite ion, and it says right here it is amphoteric or ampiprotic. The hydrogen sulfate solution can partially neutralize sodium hydroxide spills, or it can also neutralize hydrochloric acid spills. So part A and B here is just writing out the reaction, so the net ionic reaction of the aqueous hydrogen sulfite ion with the hydroxide ions from sodium hydroxide, and showing the reaction of the hydrogen sulfate ions reacting with the hydronium ions for this one right here. So basically what you're doing is just showing the neutralization reactions. So I just want you to pause this video and see if you can get them. Just to kind of start off, we know we're taking the hydrogen sulfite ion. For part A, we're reacting with the hydroxide ions from sodium hydroxide. So you need to figure out what is going to act as the acid and what is going to act as the base. And just so you know, remember, hydroxide is the strongest base possible, whereas hydronium is the strongest acid possible. All right, so see if you can figure out the way these reactions go, and the answer is going to go up in 3 seconds. And your answer should look something like this. Of course, because we're neutralizing the acidic and basic properties, we are producing water, which that's where that whole neutralization comes from. Where we're neutralizing it, we're just producing neutral water. Now, the next thing, or the last thing that we're going to do for this lesson, is to go back and look at the whole thing conjugate. So what does this mean, and where does this term come from? So we just looked at trying to classify things as either acting as an acid or a base in the reaction. Now we're going to do the same thing. We're going to look at how something acts as either a conjugate acid or a conjugate base, or defining the conjugate acid and base pairs. So what that means, the conjugate acid and base pair consists of two substances that differ only by a hydrogen. So for example, HCO3- and CO3- So these differ in only a hydrogen. So conjugate acid and base pairs appear opposite to each other in the table of relative strength of aqueous solutions on page 8. For example, that HCO3 and CO3-, how we know they actually pair up together is that when you find them in your data booklet, HCO3- and CO2- So that's why we have our acid and base conjugate pair. And that's why up at the top of our thing, or our chart, we have conjugate base formula. So we have something acting as an acid, and once it acts as an acid, it's going to act as a base in the reverse reaction, or it's going to be the conjugate base. So we're going to look at how that actually works. So for example, if we have an acid on one side of the reaction, and the conjugate base is going to be on the other side. So what that means is that generally, if we have something acting as an acid in the forward reaction, the base in the other, the acid now, so we tell here HA and we have A over here, if we look at the reverse reaction, now this is acting as the conjugate base, whereas the H3O plus is going to be the conjugate acid. So you can tell, just look, in the forward reaction, we get the hydrogen going from the acid here, and in this, it goes here, right? Acid base, but because we're referring to the reverse reaction, that's where we're going to be using the word conjugate. So acid and base referred to the forward reaction, conjugate refers to the reverse reaction. So this is just a generalization on this page, where this is one example where we can tell the way this reaction goes. We can see the HCl is donating the hydrogen over here. So in the forward reaction, we have the ammonia acting as the Bronsted-lowry base and the hydrochloric acid acting as the Bronsted-lowry acid. But in the reverse reaction, now it's the ammonium ion that's acting as the conjugate acid, and the chloride ions acting as the conjugate base. So that's why you do have to differentiate, and we're going to use these words because where everything's going to be in equilibrium, right? Our double arrow, we know that there's forward and reverse reactions, so we need to identify if we're talking about the forward reaction or the reverse. So our next few examples is just predicting or writing everything in. So we're going to define things as acid, base, conjugate acid, and conjugate base based on the reactions. So, for example, in our first one here, we got acetic acid and cyanide ion in the forward reaction. So we can tell by looking over here, the hydrogen is leaving the hydrogen acetate and going to the cyanide. So that's our acid, and this is our base. Whereas the reverse reaction, we can tell that the hydrogen leaves the cyanide and go to the acetate. So this is the conjugate acid, and this is acting as the conjugate base. So we have our acid and conjugate base, and conjugate acid pairing up. So your role right now is to go through our example right here, label things as acid, base, conjugate acid, and conjugate base. So pause the video and give this one a go, and the answers are going to come up in 3 seconds. And this is kind of how they look. So we have acid, base, conjugate base, acid, base, conjugate acid, and acid, base, conjugate base. Now I like using the arrows just to make sure I know which one I'm talking about, but you'll notice that every single time when I'm doing the reverse reaction, we use the conjugate forms, and the forward reaction just either acid and base. For example 2, of course, once we get into actually predicting the products like here, we can actually tell. It is very handy to know what a conjugate will look like depending on what we are dealing with. So for example, when you see something like HF, right? We can tell at hydrogen fluoride we don't see any negative charge here, so there's no chance for this to actually be a base. So it needs to be an acid, which is hydrofluoric acid. So the conjugate, if this is an acid, the conjugate base is going to look like this. Right? It just lost a hydrogen. The same thing, NO3 minus, we'll notice that there is no hydrogen here, so it cannot act as an acid. However, it can act as a base. So that means the conjugate acid is going to look like this. You'll notice that negative charge disappears, and it's just HNO3 minus. So just be careful about, how everything is going to look and where the charges go. So same thing, just kind of pause the video and see if you can go through all this where you get their conjugates without using your data booklet, just knowing that if something acts as an acid, it needs to lose a hydrogen ion, and if it's going to act as a base, it gains a hydrogen ion. So the answers are going to go up in 3 seconds, so just see if you can get those now. And that is what all of the conjugates will look like once you are done. All right, and of course, when in doubt as well, you can always kind of do a particular reaction. Now, I know this one right here, I'm going to just toss you for a loop, says N2H5 plus, but because it has this excess of hydrogens, that plus charge, that's why it's going to act as an acid in this case right here, because it doesn't have a negative charge, so it can act as a base, right? There's nothing to attract that extra hydrogen. All right, so our last one, or our last few examples right here, we just have write the chemical equation showing the hydrogen sulfate ion HSO4 minus acting as an acid in the presence of hydroxide. Show how the hydrogen sulfate ion can act as a base in the presence of HF, and see if you can get this diploma example as well, where it says in the list of chemical species above, H2BO3 and blank would form a conjugate acid-base pair, and the amphoteric species are blank. So just pause the video and see if you can give them a go. But in 3 seconds, these are going to go up, and then once again, I'm going to scroll down and have the answer for 35. So see if you can get those. Pause the video because the answer is going to go up in 3 seconds. All right, so for our 2 examples right here, this is how it's going to look. Of course, hydrogen sulfate acting as a base. That's why I have it labeled as base, and that's the acid. So we have the hydrogen going here. So that's why we're left with our conjugate acid H2SO4, conjugate base F minus, and same thing up here. When we label something as acid and a base, we can see the hydrogen traveling. Now for our next one, we got H2BO3 minus. So the conjugate acid and base pair, so looking at this right here, it has 2 hydrogens and a negative charge. This H2BO3 is amphoteric or amphiprotic, meaning that it can act as both an acid and a base. So in saying that, looking at our examples right here, so we have this guy H2BO3. Now if it acts as an acid and loses a hydrogen, it's going to form here, right? But if it acts as a base, it's going to form 1. So right away, C and D are our only options, so we scratch out A and B. And when we read the rest of the question, it says the amphoteric species listed above are, well, remember amphoteric we're looking for having a hydrogen and a negative charge to attract it. So this one here can only act as an acid, this one's only a base. So we got 2 and 3, so our answer is D. Now that is it for this particular section. So our next lesson, we're going to look at acid and base strength and how to predict these acid and base reactions. But before you do that, just make sure to get plenty of practice with identifying these acid bases, conjugate acids, and conjugate bases before you fire up the next lesson where we are going to be looking at using a 5-step method to predict reactions. All right, so that is it for today. So make sure to do your working workbooks, and I'll see you guys for the last lesson for this week.